We're just looking at vertical asymptotes, horizontal asymptotes. We're going to look at how to find a slant asymptote today, and then graphing rational functions. Then the plan is to hopefully get into nonlinear inequalities and solving those. And we'll have the tools by looking at graphs, but we'll also have tools that we can solve these algebraically. So just kind of a recall of how we find vertical asymptotes. So we're looking at asymptotes and how to find them of a rational function. And so a rational function, recall, this is going to be in the form where you have a polynomial in the numerator. And recall how we wrote polynomials before by that definition, a sub n, x to the n plus a to the n minus 1, x to the n minus 1, plus dot, 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 dot. A sub 2 x squared plus a sub 1 x plus a sub 0. Where our denominator, let's do it, b of m, x to the m plus b to the m minus 1. So this x to the m minus 1 plus dot, 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 b sub 2 x squared plus b sub 1 x plus b sub 0. So that was just a definition of a polynomial with certain conditions that our exponents were whole numbers and our coefficients are real. And so vertical asymptotes, so those occur values that set the denominator equals 0, but not also the numerator. So if it set both of them equal to 0, it still can't be in our domain because it sets our denominator equal to 0, but it won't have a vertical asymptote there. If it sets both of them equal to 0, then we have a hole in our graph at that value. So vertical asymptotes occur when x equals a number such the denominator equal to 0, but not also the numerator. So this is just kind of review. We already talked about all this on Tuesday. Again, if they set them both equal to 0, we had a hole in the graph. So horizontal asymptotes, that had to do with the degree of the numerator and the degree of the denominator. And there was 3 different possibilities that could happen. So horizontal asymptote. So if the degree of the denominator, if m, because that's the degree of the denominator, and the degree of our numerator is n. So if m is bigger than n, the degree of the denominator is larger, then we have a horizontal asymptote at y equals 0, the x-axis. If the degrees are the same, so if m equals n, then we have a horizontal asymptote y equals a sub n divided by b sub n. So same value of our degree. We're looking at the leading coefficient of the top divided by the leading coefficient of the bottom. If n, the numerator is the bigger one, is greater than m, then we do not have a horizontal asymptote. Okay, so slant asymptote or oblique asymptote. So those are just the same thing, just called different in different books. So I was misguided, or maybe not misguided, but maybe misled you last time, saying that slant asymptotes, well, I know those occur when the degree is larger in the numerator. But I was saying it could happen, you could have a line, or you could have other different functions like a parabola, a cubic. They're telling me that they're only slant and oblique asymptotes if the degree of the numerator is just one larger than the numerator. So this occurs if the degree of the numerator, let me see, let me just say, how about write it this way? If the degree of the denominator is equal to one more than the numerator. Okay. If we want to find these, we have to use long division. And so to find the slant asymptote, so y is going to equal ax plus b. This is the quotient of the numerator divided by the denominator. We don't have to worry about looking at the remainder over the divisor when we rewrite it, because that denominator is bigger, the degree is bigger, and it's so when it's going to infinity, then it's either shooting off. Sorry, when it's going to infinity, I just need to think and not. I need to stop and just talk and stop thinking while I'm trying to talk at the same time. So if we're looking at the remainder, you're going to get something like 1 over the, or remainder over the divisor. This piece, as x goes to positive or negative infinity, that piece goes to 0. So we can ignore that piece when we're looking at the slant asymptote. So let's just kind of go back to this vertical asymptote and just recall what the graph would look like if you had a vertical asymptote. So basically, if we have some graph here, and we say, let's say x equals a was a vertical asymptote. When we were graphing it, we denoted asymptotes by dotted lines. Normally you don't see them on the graph, but it's there and it helps you just guide you. And so what's happening here as x is approaching a from the left, it's going to be either shooting upwards to positive infinity, or it could be shooting downwards to negative infinity. But what's happening as we get closer and closer to this value of x equals a, it's going to never get to that value, x equals a, and it's going to just go start hugging that vertical line. So same sort of idea when we're coming in on the right-hand side of x equals a, the graph is either going to shoot downwards, going to negative infinity, or shoot upwards, going to positive infinity. So I might have something like this. So how we wrote this, kind of using what we did with the end behaviors. As x approaches a, as x gets closer and closer to our y, as x gets closer and closer to a of our function, let's say y, this is equal to positive or negative infinity. Where the horizontal asymptotes, that was the end behaviors of our graph. So we might have some value in here, horizontal line, where what's happening in this case is as x is going to positive infinity, our graph is going to start hugging this horizontal asymptote. Or as x is going to negative infinity, it's going to be hugging this line. Let's just call it, I don't know what we want to call it. Oh. So we could write this saying the limit, I'm glad I don't have new notifications. Okay, so limit as x goes to plus or minus infinity of y, that y value is going to some value L. Where our slant asymptote, we have some linear line. It doesn't have to be y equals x, but I'm just going to do it here. And as x is going to infinity, or x is going to negative infinity, the graph is getting closer and closer to that line. It might have something like this. I have no idea. That wasn't a function. Okay, so it's going to hug that line. Okay, so let's start graphing. So graphing these are not bad at all. Graphing rational functions are actually kind of fun. So the first thing I do when I'm graphing rational functions is I find my asymptotes. So find the asymptotes vertical asymptote, if it exists, the horizontal asymptote, if it exists, or the slant asymptote, if it exists. If a horizontal asymptote occurs, I know a slant asymptote does not occur. If a slant asymptote occurs, then a horizontal asymptote is not going to occur. So only one of these can happen. Possible. So it's possible neither happens. Okay, so once you've found those asymptotes, then find your intercepts. So find your X and Y intercepts, again, if they exist. Sometimes it's helpful to figure out what your domain is. And then you want to graph things. And so we're going to graph the asymptotes. And plot a couple additional points if needed. On each side of a vertical asymptote. Okay, so from there, usually you can see what's going to happen with a graph as it gets closer and closer to a vertical asymptote. Is it going to shoot up? Is it going to shoot down? We can also see what's going on as X is going to infinity or negative infinity. I'll keep that there while I pull an example. So your book, it talks about graphing rational functions. I'm combining two of these sections together. Remember 5.3 and 5.4, graphing rational functions. For 5.3, they talk to you about using transformations of functions on 1 over x. So maybe let's just look at that real quick. So if we have y is equal to 1 over x, let's recall what that looks like. So if I look at this, I know that the only value that sets the denominator equal 0 is 0. And that does not also set my numerator equal 0. So I know we have a vertical asymptote at x equals 0. So we have a vertical asymptote. And x equals 0. So horizontal asymptote, if I look at the degree of the numerator, there's no variable x here. The degree of the numerator is 0, and the degree of the denominator is 1. Degree of the denominator has a larger power than the numerator, and so the horizontal asymptote is going to be at y equals 0. If I look at finding intercepts, I notice that they don't occur. The numerator is never going to equal 0. And that's where our x-axis or x-intercepts would occur. And then there's no way to figure out what value sets x equal to 0. Y is never going to be, you can't solve for it. It's undefined there. So no intercepts. Okay, so we actually saw that these were asymptotes, these x and y axes. So I know the graph is going to be hugging this line as I get closer and closer to x equals 0. And I know as x is going to positive or negative infinity, that's going to be hugging the x-axis. And so I just need to plot a couple points to see what's going on. And so let's plot a couple points on the left-hand side of this vertical asymptote. So if we plugged in -1, where I see an x here, right? I get 1 over -1. I see my y value is also -1. So I have a point here. If I plugged in, let's say, -2 there for x, 1 over -2 is -1/2. So just by those points and knowing where those asymptotes are, we can see what's going to happen here. We're going to get closer and closer to this as x goes to negative infinity. But if I plugged in 1/2 in here, -1/2, 1 over -1/2 is -2. So this is shooting down to negative infinity. This is actually an odd function. So odd functions are reflected across the origin. And odd means, recall, if I plugged in -x for wherever I saw an x, this would be the same thing as if I had -y. So we can use that fact and plot other points, or we can just go in and plot it. So if x equals 1, I get 1 over 1, have 1. If x equals 2, I get 1 over 2, which is 1/2. If x equals 1/2, I get 2. So my graph on the right-hand side of that vertical asymptote has to look like this. So now, knowing this graph, we can use this to help us graph using transformations. There we go. Okay, so graph the rational functions using transformations. So what if we had y is equal to 2 minus 1 over x plus 1? Okay, so we got to figure out what this 2 is doing to our graph, what this minus is doing, and then this plus 1 is doing. I don't know if it would help you if you rewrote the order, but this is the same thing as negative, putting the fraction first, negative 1 over x plus 1. And this would be a plus 2. So what is that plus 1 doing in here? To get that x plus 1 there, I would have to look at f of plugging in x plus 1 wherever I saw an x. So was this a vertical shift or horizontal shift? In which direction?
A horizontal shift to the left by 1.
Yep, so it's inside, so it's a horizontal shift, and it was opposite of what direction, and to pick up the slack for our x values, and so this shifts. F of x equals 1 over x to the left 1. So basically this asymptote right here on the y-axis is shifting to the left 1, so we now have an asymptote at x equals negative 1. And then we have this minus in front. So that would be putting a minus in front. So what does that do to our graph? So you're changing your y value sign. Changing the sign of y is a reflection across the x-axis. So reflection across the x-axis, right? So this is going to now not be down here. It's going to be up here. So right now we have something like this. And the one that was above the x-axis is now below the x-axis. But then we're, sorry. But then we're adding 2 to it. So that plus 2 does so this is going to shift it up 2 units. So our horizontal asymptote that used to be the x-axis, shifting it up 2 units. It's now right here. Let me get rid of the reflection across the x-axis for now. So now my graph has to be, it was reflected across the x-axis, and so now it's up here. This piece that was up here before is reflected across the x-axis, but it was shifted up, so it looks like this. So this is our graph of y equals 2 minus 1 over x plus 1. Okay, so let's review how to do long division with the next problem. So let's say you had r of x is equal to 6x squared plus 19x minus 7. And this is all over 3x minus 1. So notice our degree of the numerator, which is 2, and our degree of the denominator is 1, and the degree of the numerator is 1 larger than the denominator. And so this tells me there's a slant asymptote. Okay, so because degree of the numerator is 1 larger than the denominator, we have a oblique asymptote. Okay, so doing long division of polynomials, if you remember how to do long division of real numbers, then it shouldn't be too bad. If you forget how to do division of numbers, then you need to review that because you'll probably have a hard time. So we're looking at our divisor. That's what we're dividing by, which is 3x minus 1. Put it out here. And we're dividing into the numerator, the dividend, which is 6x squared plus 19x minus 7. So we're just looking at, when we're doing long division, we're just looking at this first term really right now. And what can we multiply this first term of our divisor by, 3x, to get this first term of our dividend? So I first think to myself, 3 times what is 6? Well, I know 3 times 2 is 6. And then x times what gives me an x squared? Well, I'm missing an x, so I need an x. So remember when you figured out what number went in? So like, I don't know. Could be something on the side. So if I was looking at 55 going into 1,970. So first thing we did, right? We look at the 55. Does it go into 1? No. Does it go into 19? No, it's too small. Does it go into 197? Yes, it goes in, and you kind of approximate. Well, I know 4 times 50 is 200. That's too big. So I guess when I say 3. And so once we did that, then we distributed that 3 to each number and put it below. So 3 times 5, that was 15. And 3 times 5 is 15 plus a 1 is 16. And we subtract it off. So 7 minus 5 is 2, 9 minus 6 is 3. So same sort of idea here, how we distributed and put it under. We're going to distribute this, and we're going to put it under here. So 2x times 3x, that is 6x squared. 2x times negative 1 is minus 2x. But we have to subtract it off. Gosh. Maybe I need to move those pins. So we have to subtract this off. But we have to subtract everything off. And so think of it as distributing that negative. And so if we do that, we get 6x squared. This will now be a minus 6x squared. So that cancels. And it should, because that's what we chose this to do. And then here, distributing this negative, this is really now plus 2x. So 19x plus 2x, that gives us 21x. So once we finished that off, like over here, and we subtracted, then we bring down our next number. So in this case, we bring down our next term. So I'm going to bring down the next term. So a minus 7. And then we do it over. We think to ourselves, what am I multiplying this 3x by to get this first term down here, 21x? Well, 3 times what is 21? Well, that's 7, so plus 7. Like here, we would think 55 goes into 3, it doesn't, 32, it doesn't, 320. My guess is 6 is going to be too big, so 5. So 5 times 5 is 25, 5 times 5 is 25, plus 2 is 27, and then we subtract off. So distribute our 7. We get 3x times 7 is 21x. 7 times negative 7 is minus 7. And we're going to subtract it off. So we have to subtract off the whole expression, 21x minus 7. So change the signs. 21x minus 21x, that cancels. And negative 7, this is really plus 7, because distributing the negative, that cancels. So we get back 0. There's no other terms to bring down, and so we're done. This actually goes in here evenly. And so we find that our slant asymptote, or oblique asymptote, same thing. Is that y equals 2x plus 7. This is our quotient. So our slant asymptote was equal to our quotient. Okay, so long division, we're going to see this again in this class when we get into partial fraction decomposition. also when we're looking at zeros of polynomials, which is actually a little bit further in this book, or in this section, or not section, chapter. You guys remember how to do that? Should we go over another one?
Yes, please.
Okay. Did it help that we showed, you know, long division on the side here with numbers to kind of recall what to do when we were doing polynomials? Did that help a little bit? I didn't finish here. I'd have to subtract. 10 minus 5 is 5. This is now 1. Borrow 11 minus 4. I'm sorry, 7 is 4. This was smaller than this, so we chose the right thing. There's no other number to come down. We could rewrite it as a decimal, or we could say this was 35 and 45 over 55.
Okay, so is the problem on the right side just to show us how to do regular long division? It doesn't have anything to do. Oh, that was actually confusing me. I was trying to figure out. I was trying to figure out where the 1970 came from. Like, where in this thing is 55? I get it now.
I'm sorry. So I just thought, oh, you know what? Maybe it would be good to kind of recall how to divide by numbers while we're doing this to show, you know, it's still the same process that, you know, you got to figure out what you're going to multiply.
Okay.
To get what's under here.
I'm much better now. Okay.
Okay, shoot. Okay, but we can still go over another one. So we got to be careful if, let's say, look at in this case. So sometimes you have terms that are missing, like this right here, our divisor, our dividend, it's descending order of powers. There's no powers missing. Where in this next example, we have terms where it's not descending in order. There's missing terms. So for instance, let's say g of x is equal to x cubed plus 1, all divided by x squared minus 5x minus 14. So the degree of our numerator, 3, is 1 larger than the degree of our denominator, 2. And so because of this, we know that there's an oblique asymptote, and we're going to have to use long division. So we're going to put our divisor out here, x squared minus 5x minus 14, all divided into. So notice that we have an x cubed and then it jumps down to our constant. And so we're missing, we can write it. It's good to put a placeholder sometimes for missing terms. So we have a 0x squared. There's a term 0x, and then let's put our plus 1. It just helps keep things lined up and organized with like terms. So all you're doing is going to the first term x squared and looking at what do I multiply x squared by to get an x cubed. It's just a single x, right? And so distribute that x to each term and put it underneath here. So x times x squared is x cubed. X times negative 5x, that gives me minus 5x squared. And x times negative 14 is minus 14x. So we got to subtract this whole thing off. So basically just changes the signs in here and add it to the dividend above. So x cubed, this is really minus x cubed, cancels. 0x squared, this is really going to be a plus 5x squared. So that gives us 5x squared. Distributing that negative, this is now positive 14x plus 0x is plus 14x. So let's bring down our next term, plus 1. So again, look at your first term, x squared, and think to yourself, what am I multiplying x squared by to get 5x squared? Well, I'm missing a 5 there. So 5, distribute the 5 and put it below. So we have 5 times x squared is 5x squared. 5 times negative 5x is minus 25x. And 5 times negative 14 is negative 60. I'm going to subtract this whole thing off. So 5x squared minus 5x squared cancels.
Ms. Noxinger,
Mm-hmm.
wouldn't 14 times 5 equals 70?
You're right. 14 times 5 is 70, so negative 70. Thank you. So this would cancel. This is now a positive 25x because of the negative. So positive 25 plus 14, that's 39. So 39x. Distributing this is now positive 70. 70 plus 1 is 71. We know we are done when this degree is less than this degree. There's no way I can multiply x squared by some term to get me 39x, a degree less than, unless I have negative exponents, but we're not going to do that. So we found our slant asymptote. This would be our remainder, but our slant asymptote is y equals our quotient, x plus 5. So notice that we didn't get a remainder of 0. So this tells me that this here, x squared minus 5x minus 14, is not a factor of our numerator, x cubed plus 7. Where that last example beforehand, it went in evenly because our divisor or remainder was 0. And so we could say our 3x minus 1 is a factor of our numerator. So we're going to use this to help us find zeros of polynomials. If this goes in evenly, then we know that that has to have, it's a factor and it would have a 0. So something to look forward to real soon. We'll get to that. Okay, so again, I want to go in and then just graph some, putting together everything that we just figured or did. Okay. So let's graph g of x is equal to x squared minus x minus 12 all over x plus 1. So we want to find asymptotes. And so vertical asymptotes, we were looking at values that set the denominator equal 0, but not also the numerator. So finding asymptotes, a lot of times it's helpful if it's not factored to factor both the numerator and denominator. And so let's just do that real quick. Well, denominator can't be factored, but the numerator can. So two numbers that multiply to negative 12 and add to a negative 1. So x minus 4 x plus 3. Okay, so they don't have any common factors in the numerator denominator, so we have a vertical asymptote. At x equals the value that sets this 0, so -1. Horizontal asymptote. Well, looking at the degrees, the degree of the numerator is larger, so there's none. And then slant asymptote, if it's just degree of the numerator is just one more than the degree of the denominator, which it is, there is one. So slant asymptote, we're going to need to do long division. So we're going to look at x plus 1 divided into this x squared minus x minus 12. So x times what is x squared? That's just a single x. Distribute. We get x squared plus x. We're going to subtract it off. So x squared minus x squared cancels. This is a negative x. This will be a minus x. So that's a negative 2x. And then bring down our minus 12. So x times what is negative 2x. So that would be a minus 2. Distribute negative 2, we get negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. And we're going to subtract this whole thing off. So negative 2x plus 2x cancels. Negative 12 plus 2 gives us negative 10. So we have a slant asymptote at the line y equals x minus 2. I'm just going to box these so when I come back to graph, they're easy to find. Okay, so now intercepts. Intercepts are also helpful. We already factored. When you're looking for intercepts, the x-intercepts, it's when the numerator is equal to 0. We don't have to worry about the denominator. So x-intercepts. So I'm looking at when my y value is 0, this is equal to, I'm going to put it in the factored form, x minus 4 all times x plus 3 all over our denominator x plus 1. But we can clear our fraction rate by multiplying both sides by x plus 1. 0 times anything is 0. So this is equal to my numerator again, x minus 4, x plus 3. So we have x-intercepts at x equals 4 and x equals negative 3. Same kind of idea when we were graphing the rational, or not the rational, the polynomials, not the rational functions, and we had multiplicity. That told us if it crossed or touched. Same sort of idea here. If this is an odd multiplicity because our powers were odd of our factors, this tells me it's going to cross at the the x-axis and not just touch and turn around. And then y-intercept. Well, that occurs when x is 0. So if we look at g of 0, go in there and plug in 0 wherever we see an x. Well, it doesn't matter. I have the factored form up here, so I'll just do it. So I have 0 minus 4 times 0 plus 3 all over 0 plus 1. So simplify -4 times 3 in the numerator gives us -12 all over 1, or -12. Okay, so let's put this all together. We had a vertical asymptote at x equals -1. We did not have a horizontal asymptote. We had a slant asymptote at y equals x minus 2. That's a linear equation. We know our slope is 1 and our y-intercept is -2. So a point at 0, -2, and if I rise 1, I would go over 1. Rise 1, go over 1. So I got my graph that looks like this. And then we had x-intercepts at 4 and -3. That was 2, 3, 4. And we had a y-intercept at -12. Okay. So I told you how we should look at couple points on each side of a vertical asymptote. Notice that we already have a couple points on this right-hand side. And so knowing where my asymptotes are, that vertical asymptote right here, this graph on the right, this has to be coming down here. I know it's not coming up because that would tell me that I would have an x-intercept in here, and it's not. And I know it can't cross this line, so it can't come back, cross a vertical and come up here. So because of where this vertical asymptote is, where this point is and this point is, I know my graph looks like this. And it's because of my units are kind of not on scale for the x and the y, so it kind of looks funky. I don't know how I want to do this kind of like this. So I only have one point here. I know it crosses. So it could either come up like this and hug it like that, Or I guess it could go like this, but I doubt it because of this asymptote. But let's just plot one other point. So how about -2? So let's go in and look at what g of -2 is. Okay, so doing that, plugging that in wherever you see an x, you got -2 minus 4, all times -2 plus 3, all over -2 plus 1. So our numerator, we have -6 all times 1, all over -1, which is equal to +6. So when x is -2, we have y is +6. I'm sorry, why did I put that there? It's not an X-intercept. Okay, so knowing where this is, knowing I had all odd multiplicity I was crossing. And so we're going to come down and we're going to end up eventually starting to hug this line. So being able to figure out where your asymptotes are, your intercepts, and maybe 1 or 2 additional points, you can kind of get a general sketch of what your graph rational function would look like. Okay. Hopefully you can see that.
It looks like there's symmetry between the asymptotes. Is that something that occurs?
So it'd be hard to tell. Yeah, there could be. It's just like, though it's not like a symmetrical across the x-axis or the y-axis. I'm wondering it. That's a great question. And I don't know if I know the answer to that. It does look symmetrical, but I don't know how to say what it would be symmetrical across. Is it symmetrical across this line? So I'm not sure.
I just think there's an interesting thing that would help us figure the points out through symmetry. But
so if our vertical I mean, we could look at you know, even odd. So I could look at, is f of -x equal to -f of x? If so, this would be symmetrical across the origin. And then I know that if xy is a point, then -x, -y is also a point. Or I could see if it's even, does even f of -x equal f of x? If so, it's even. And so if I have xy on a graph of that, then also -xy is a point. So we could look at even odd and go about it that way to just get additional points. But I don't think that this function is either even or odd. It's not. Okay, so let's stop there for now and take a break. Okay, so we're going to start looking at the inequalities of rational functions and polynomials. And so when we're looking at inequalities, solving inequalities and they're not linear, we have to approach it a little differently. We looked at quadratic inequalities earlier in this course, and we looked at graphing them and then seeing, you know, was it less than 0, greater than 0, falling above the x-axis or not. And so let's look at the following example. So we want to solve for r of x less than 0 where r of x is equal to the rational function x all over parentheses x minus 1 and your parentheses and times parentheses x plus 2 and your parentheses. So it's saying when is r of x less than 0? And so we're looking at r of x as another way of saying when is our y value of this function negative. So when is y negative? So we're looking at what values of x make all our y values negative. So let's graph this, and then let's find out when is this graph of r of x below the x-axis. And so let's find our asymptotes. And so looking at vertical asymptotes, those are again values which our denominator equal to 0, but not also our numerator. And so x equals positive 1 sets our denominator equals 0. And at x equals negative 2. So I just want you to be careful when you write and I ask you on a test, what is the vertical asymptote? Don't just give me the number. These are equations. And so vertical lines, remember, are in the form of x equals a number. So looking at this horizontal asymptote, well, if I look at the degree of my numerator, this is degree 1. I can't see the degree of my denominator without thinking about distributing this out. But if I distribute this out, the highest power is going to be an x squared. And so the degree of my denominator is 2. It's larger. So I do have a horizontal asymptote, and it's the x-axis. So y equals 0. So if it has a horizontal, it does not have a slant. And then intercepts. So if we look at plugging in 0 wherever we see an x, we can get our y-intercept. So go in here. We have 0 all over 0 minus 1, all times 0 plus 2. So this is 0 over negative 2, which is 0. And I can see that my equation is equal to 0 for my y-intercepts when x is also 0, which makes sense because it's the origin. Clear a fraction, we get x equals 0. Okay, so let's put what we have down now. We have our asymptotes, the x-axis. Our y-axis, and then we had asymptotes at x equals 1 and x equals negative 2. 2, excuse me.
And then we also had a point on our origin. Okay, so I don't know what's happening yet. I know though that my degree or my multiplicity of 0 is just 1. It's odd, so it's going to be crossing. But is it going to be crossing like this or like this in here? I also know that this is my only x-intercept. And so I'm either going to stay above or below the x-axis, depending where my points are. And so let's start plotting points. And so let's choose a couple points on each side of our x equals -2, or actually just 1 point works. So let's say x equals -3. So if we go back in here and we plug in -3 into our equation, that would give us, let's see, let me just do it over here. So r of -3 is equal to -3 all over -3 minus 1 times -3 plus 2. So reducing, we get -3 in the numerator all over -4 times -1, or 3/4. So x equals -3, we get -3/4. So again, with the reasoning of where our horizontal asymptote is, where our vertical asymptote is, finding the only x-intercept, this has to be below. And so it has to hold, shoot downwards as x approaches -2 on the left. And then as x is going to -infinity, it's going to be hugging the x-axis. So same sort of idea. We have 1 point in here. We need at least 1 more point. So let's look at what's happening at x equals -1. So if we plug in -1 wherever we see an x and r of x, so we have r of -1. So we got -1 all over -1 minus 1 and -1 plus 2. So this is equal to -1 all over -2 all times 1. So -1 over -2 is +1/2. So x equals -1, we had +1/2. Okay, it can never cross a vertical asymptote. We know that there's no x-intercept right in here. And so this piece has to be coming up and hugging and going off to +infinity as x gets closer and closer to -2 on the right. So this can either come up like a parabola shape kind of, or it's going to come down. And again, because I know the multiplicity of my 0, I know it's going to cross, but let's just show it. So let's just show that if we plug in +1/2, this would give us a negative number under there. I really don't care what number it is. I just want to show it's negative. So if I plug in +1/2, so r of 1/2. So that's my x, which is 1/2 all over 1/2 minus 1 and 1/2 plus 1.
Isn't that supposed to be +2, not +1?
Yep, say, yeah, +2. +2. So numerator's positive, right? 1/2 is positive, all over 1/2 minus -1, that's -1/2, but it's a negative number. All times 1/2 plus 2, which is positive. So notice that positive over a negative is negative. And so I really just wanted to show that it was going to be below the x-axis there. So when x is positive 1/2, we fell below the x-axis. So the graph is going to be looking like this. Okay, so one other thing that we got to check is on the right-hand side of x equals 1. So because we know it doesn't cross the x-axis here, it's either going to look like this on the top, or it's above the x-axis, or it's going to look like this on the bottom because of below the x-axis. So again, we just need to choose one point on this side of x equals 1, plug it in to see, do we have a positive or a negative value? So R of 2, and it doesn't hurt to get that value. I just don't want to deal with fractions. Really. So we would get 2 in the numerator all over 2 minus 1. 2 minus 1, which is 1. And 2 plus 2, which is 4, which is 1/2. So when x equals 2, we have a value of 1/2. So it's above the x-axis. So this whole graph has to be above the x-axis. Okay, so we got the graph of it. And hopefully that kind of, again, solidified what we're doing today with graphing rational functions a little bit earlier. But now we want to figure out when is r of x less than 0. So when is this graph falling below the x-axis? So it's falling below the x-axis right in here. And it's below the x-axis right here. And so all the x values that you're hitting, because we're looking at the x values that make y less than 0, we're looking at all the values coming in from -infinity to -2. Union, then we're hitting all the values from 0 to 1. Let's make this go one step further. Let's ask one more question about this graph. What if it had been find when r of x is less than or equal to 0? So the only thing I changed here was I put the equal to part. You've got to be careful. You can never have an x value. It's not part of the domain if we have a vertical asymptote. So x equals -2 is not defined. It's not in the domain. So we do not include that value when we look at values less than 0. So -infinity all the way to -2. We don't include it, so we put a parentheses. Union. But notice that this x equals 0, that does set the whole equation equal to 0. And so that is a solution. So we do include it 0. So we have a bracket 0, comma. But again, vertical asymptotes, it's not part of our domain. X can never be 1. So when we say all values where this graph is below the x-axis, it's till you hit 1, but not including. So when you're doing, so the main point is, if you have an equal sign in that inequality, you got to be careful to not include values what set the denominator equals 0, but to include the values what set our numerator equals 0. So kind of think about this, and this is how we would solve this algebraically. There were important points that we looked at when we were looking at this graph. We were looking at intercepts, because that's where it could change from above or below the x-axis for our x-intercepts. And the other place where it could change above or below the x-axis were at our vertical asymptotes, because it couldn't cross that vertical asymptote, so that graph can jump above when it was already falling below. So basically, those are basically our critical values or critical numbers that we are trying to find, and then we can just plug in a number to the left of that to see if it's positive or negative, to see if that inequality is true or false. So that's what we're going to do. And we're going to test points on each side of these critical numbers, your x-intercepts or your asymptotes, into the inequality to see if it's true or false. Any place that it was true, then that's part of our solution. Any place that's false, we exclude that interval from our solution. So I want to do another one with the graphing and just, again, kind of reiterate why we're looking at those critical numbers. So let's say that you have the following. X plus 1 all over x minus 3 is less than or equal to 2. We have to be careful here. A lot of times students want to just cancel, get rid of their denominator by multiplying by both sides. The problem with that is that our denominator has a variable, and that's where our asymptotes are going to occur. And so you're going to exclude that value when you do that. And so when you're solving these, first thing that you want to do when it's a rational inequality, you want to get everything to one side of the equal sign. One side of the inequality, not equal sign. And then if it's rational, we want to rewrite it as a single fraction. And rewrite it as a single fraction. Okay, so let's do that first. So here we want to get this less than or equal to 0. Let's subtract 2 on both sides. And so we can rewrite this inequality as x plus 1 all over x minus 3 minus 2. I'm going to leave a little bit of room because I know I'm going to need a common denominator so that I can multiply that by fancy 1 is less than or equal to 0. So I need a common denominator in order to add fractions. So our LCD of x minus 3 and 1 is x minus 3. Let's multiply this by our fancy 1, x minus 3 over x minus 3. So we have x plus 1 all over our new denominator of x minus 3. Let's distribute. Make sure if there's a minus in front of your number that you distribute that minus. So you have a negative 2 times x, or a minus 2x. And a negative 2 times a negative 3 is plus 6. bring down the less than or equal to 0. So let's combine like terms in our numerator. We have an x minus a 2x is negative x. We have a 1 plus 6, so plus 7, all over x minus 3 is less than or equal to 0. So once you've done this, you want to, sorry. We want to find our critical numbers, but I want to go through the graphing portion of this. So okay, so critical numbers, and I kind of stated it before, let's just write it. These are numbers that set the numerator equals 0. And numbers that set the denominator equal to 0. Numerator is equal to 0, those are your X-intercepts. Denominator equals 0, vertical asymptotes. Or holes. So those are the places where it could be changing above or below the x-axis, and those are the values that we have to worry about. For us though, let's graph. So we can get practice on graphing. Let's graph y equals this rational function negative x plus 7 all over x minus 3. So I noticed that we have a vertical asymptote, value that sets my denominator equals 0 is 3, and that doesn't set my numerator equals 0. Horizontal asymptote, it exists because the degrees are the same. It's the leading coefficient of the top, which is -1, all over the leading coefficient of the bottom, which is 1, or y equals -1. That doesn't really help us if we're looking for critical numbers, but it's going to help us graph it. And then intercepts. Well, what sets our numerator equals 0 is when x is positive 7. So I know I have an x-intercept when x is 7, y is 0. And if we plug in 0 for x, that's going to give us the y-intercept. So I get positive 7 over -3, so -7/3. Or just because it helps me to graph it, to look at that as more of a, as either a mixed number or a decimal. So 3 goes into 7 twice, so this is -2 with a remainder of 1, so -2 1/3. So I'm just going to graph what we have. We got our vertical asymptote at x equals 3. We have a horizontal asymptote at y equals -1. And we have a y-intercept at -7/3. Oops. which is -2 1/3. So about here. And we have a X-intercept at 7. So 4, 5, 6, 7. So pretty much I actually know exactly what my graph is going to look at like because of those 2 points that we found and those asymptotes. This graph has to, it's odd multiplicity. So the graph is going to cross and it's going to start hugging this. And then it's going to come down here and it's going to start hugging this line y equals -1. And then down here, because this point's down here, I'm never going to go back up and cross my x-axis. So it's going to have to look like this. So when you find your critical numbers, our critical numbers would have been, like I said, when our numerator is equal to 0, which was 7. And at our vertical asymptote, 3. So if you were doing this without graphing the whole function, you could, and you would find those critical numbers, place them on a number line, that's how I do it. And then we want to test a number on each side, just one, of our critical numbers to see if it's positive or negative. Does this inequality hold true or not? So our original inequality, where is it at? Was x plus 1 all over x minus 3. Is this less than or equal to 2? Or as long as we didn't do any math wrong while we were moving things to one side, we could look at -x plus 7 all over x minus 3 is less than or equal to 0. So test points. So choose something on the left of 3. So let's say let x equals 0. If we plug this into this inequality, would this make it true or false? I know by looking at the graph, this should be a true statement. It's below the x-axis. But if I didn't have that graph there, plugging it in, I get 7 all over -3. Is that less than or equal to 0? And it is. So this is true. Any number to the left of 3 is going to be part of my solution. Choose a number between 3 and 7. So if I chose a number between 3 and 7, well, looking at my graph, right, I'm telling you it's above the x-axis. But if I didn't have that graph, I would choose a point in between this 3 and 7 and plug it in. So let's say x equals 4. So if I plug in 4 into this equation, would it be a true statement or a false statement? So I get -4 plus 7 all over 4 minus 3. Is this truly less than or equal to 0? Well, -4 plus 7 is 3 all over 1. This is not less than or equal to 0, so this is false. Choose a value on the right of 7, so x equals 8. By our graph, we're saying it's below. This should be a true statement. So if I plug in 8 in here, I get 8 plus 1 is 9, all over 8 minus 3 is 5. Is this less than or equal to 0? Oops. Sorry, when I plugged in 8, this is -8 plus 7. I don't know where I got 9. I was looking up here. -8 plus 7 is -1. Is that less than or equal to 0? That's true. So our solution are from negative infinity to 3. Can never include a vertical asymptote. So a parentheses union. And then everything from 7 to infinity. And we have the equal to part. This 7 makes it equal 0, so we include it. So bracket 7 to infinity. Okay, so we actually looked at the harder point with looking at rational inequalities before we even looked at polynomial inequalities. But polynomial inequalities should be also reviewed from a previous course. So I'm going to keep 5.5 as homework. That's due on Tuesday. So this week we covered 5.3, 5.4, right? And 5.5. I apologize for keeping you guys a couple minutes after.